the delay. So welcome to the Brazilian ICPC Summer School 2025. I'm Rafael Choeiri, I'm the director of the school. I'm going to do a small talk before passing the word to our instructor. So this year, as always, the Brazilian ICPC Summer School is promoted by Sociedade Brasileira de Computação, the Brazilian Computing Society, and Maratona de Programação, our branch of ICPC in Brazil. It's organized by Unicamp and the Institute of Computing. And we have some sponsors that make this school possible every year. So this year we have Huawei as a premium sponsor. We have Unicamp as a gold sponsor, Neon as a silver sponsor. As bronze sponsors we have Google, Profusion, and Intech. And if you take a look at the logos, you're going to see some balloons next to them, some purple balloons. This is the number of female students that this company helped to pay to be on the school. So we paid for some female students to be on the school, paying their trip and some money, some stipend. So Unicamp helped us pay for 5 female students, Neon, Google, and Intech 1 each. So just some numbers of participation. Going back to 2012. So in the beginning, the school was made for ICPC finalists. Maybe we can cue these lights. It's hard to see. Yeah, thank you. Someone can do the same on here. Yeah, it's better to see now, yeah?
Okay.
Yeah, it's okay. No. Thank you. So we had some ICPC finalists. I don't know why the numbers are not showing. So we have some ICPC finalists and other students. So we in 2019, we opened another class, the Brazilian final class, so the number of students grew a lot. And stayed that way. Our peak was during the pandemic when the school was online, and now we have a steady number of participants. And now we're going to have a transition because we are going to have students that are Programadores de Américas participants that we don't know yet if they are ICPC World finalists or not coming to the school. So last year we had some World finalists and some Latin finalists. In these years we have like 73 Latin American finalists participating in the school. So most of people on this class is going to Salvador in March. Yeah? So who's going to Salvador in March? Okay. Oh, yeah. Mm-hmm. We also have some people from Olympics in this class and some other students as well. From our students, so we have people from Argentina. Okay, nice to see you guys. Bolivia. One guy from Bolivia. Brazil. Okay. Chile. Hi, Chileans. Colombia. Okay. Costa Rica. We have one student from Costa Rica for the first time, I think, in the school. Nice to have you here. Mexico. Okay. Peru. And Uruguay. Okay. Very nice to see people from all over Latin America here in Campinas. We also have students from several Brazilian states in the school. So this is a map with a pin for each student that we have in the school. This is a graph for female participation. Sorry, again, I don't know, when I export to PDF, I lost the numbers. But in 2019, we had only 8 female students in the whole school. Now we have 43 female students, and we started to fund some of them to come to the school, paying for their transportation and helping with some costs. And in that way, we could increase a lot the participation. We also made every female student exempt of the registration fee. We want to see this number grow each year. I couldn't do that a lot in the last 3 years, but let's hope this graph can improve with time. So these are the instructors from both classes. So we have Franchitek, or Frank, he told me how to call him. And, oh my God, this is wrong. Sorry. Okay. Sorry. We have Zolt on the second week. Michael Forsek was the instructor from last year. And we have 4 really good competitors on the Brazilian final class. So what's the schedule? So you wake up, you come to the lecture at 8:30 to 11:30. You're gonna have a coffee break on the side of the room here at the time that the instructor wants, but around 10. Okay. Then, if you have your badge, don't lose your badge. You're gonna have lunch at the university restaurant, and then you come back, and you have your contest during the afternoon on the labs here. And then, if you have your badge, you can go to dinner at the university restaurant. And then you can go to sleep. If you don't have your badge, you can go to sleep hungry, okay? Especially if you didn't have lunch. And then you wake up and you repeat this Monday, Tuesday, Wednesday, Thursday, no, Friday and Saturday, okay? So except for Thursday and Sunday, this is your schedule for the 2 weeks. This for the Brazilian final class. And we have some other activities. So on Wednesday at night, for the female participants, we have an event called Woman in the Summer School. It's gonna be here at 6:30. Instead of going for dinner at the university restaurant, it's gonna be food here for these female participants, okay? On Thursday, it's sponsor day. So you're gonna have a talk of by the Institute of Computing. It's gonna be in a different location called Ciclo Básico, because it's a big room that can fit both classes at the same time. Okay, the location is on the website. I'm gonna also send in the Telegram group. Join the Telegram group, please. The announcement is going to be there. There's going to be a coffee break at the location before starting at 10. Okay, so you can arrive for the coffee break and then stay for the talk. Then you're going to have lunch in the university restaurants, and then you're going to come back. You can use our facilities during that time. But you're going to have a talk with Carlinhos at 2 for the Word final class and at 3 for the Brazilian final class. And then at 4:30, I'm gonna have a coffee break afterwards, and at 4:30 we have a soft skill workshop. It's with limited spots, so the ones that want to register, want to participate, needs to register in the form until today. Okay, I already sent the link on the group. I'm gonna send it again for those that just entered the group on Telegram. Okay. So because it's going to be on this room, and this room can only fit like a little less than 100 people. On Saturday night, after the contest, in your case, we are going to have a pizza party out our bosque or woods. I don't think it's a woods, but people here call it that. Which behind this building. Okay, so there's going to be a pizza for everyone to eat, and maybe some karaoke here at the auditorium. Okay, if we can get the equipment to work this year. On the other Thursday, it's going to be sponsor day again. There's going to be a conversation circle for women and non-binary students, like similar to this one, but focus on this specific group. And in the afternoon, we're gonna have a talk by Neon and some activities. But we are going to have a coffee break before 10:30. We are going to have lunch at University Restaurant and dinner at University Restaurant. This doesn't change. This is equal every day. Okay? Okay, so just to finish, I like to thank our sponsors, our instructors that sometimes come a long way to teach, the Institute of Computing of Unicamp, SBC, all of the organizers, that a lot of organizers helping the school to happen, and our staff members. Please, if you have any problem, search for staff members. They are usually around here preparing the coffee break, and they can help you with anything that you need. But please also write to me, find me, talk to me or other organizers, okay? So this is our Telegram group. You can also write to us at maratona at ic.unicamp.br. I already added you to these Google groups for future communications. And please follow us in our social media. We are going to post a lot in the Instagram during the week. So repost. You can also tag us so we can repost things that you published and so on. Okay. And later on, I'm gonna also send you a link for a Google Drive with the photos that we are taking. So maybe it's not published on the social media, but there's some photo of you that you want to save and so on. Okay, any questions? Yes.
Are you going to stream the classes and so on?
Yeah, we are streaming the class live on YouTube, on the Maratona de Programação YouTube. Okay, so hi to everyone in the stream.
Okay.
Well, what does soft skills mean? Or like
Lucy?
what does it entail?
Lucy, what's the workshop of soft skills entails?
We start 6:30 p.m. We have 100 slots to participate.
But what's going to be taught? It's going to be, what's the subject?
We will talk about the creativity, curiosity, leadership, anything like this. We have, I think, 2 enterprises to do the soft skills workshop. We will have a coffee break too. I think this is very interesting because we need these soft skills to work to do these things at work.
Okay, so have a nice class. Thank you again. precisa fechar o projetor, né? Huh? Yeah, it's going to turn us on this side and turns off on that side. I don't know.
Não pode ficar parado.
Combater o sedentarismo, né?
Tem que acender as luzes. Tá? Should turn the light.
Can you please turn back the lights? Yeah. So about the coffee break, you can like do the time you want. Around 10. So early is bad for us because we need to prepare the food.
Okay, yeah. Roughly up to.
Yeah. Okay.
In a second, it's gonna.
Okay, so hello everyone. My name is Franciszek. I'm from Poland, but like you can call me Frank. I know Franciszek is very hard to pronounce. And I'm gonna like, give lectures here during this week, and also I prepared some like, contests for you. You can add me on Telegram. Is like this text visible for everyone? Okay, so you can add me on Telegram in case like you need help with solving problems. You have some like programming or non-programming questions, want to play board games, whatever. You can just contact me. Okay, and usually like on those lectures, like except today, we will be having some like in-depth analysis of selected problems from the previous day contest, except today because there is no previous day contest. So today I'm going to talk a bit about like my insights on contest strategy, and then talk about fast Fourier transform and its various applications and tricks. Okay, so some technicalities first. So I think there is the link to join the contest on the Telegram group, and I would like to ask you to join this contest like not 5 minutes before the contest, because I need to approve everybody manually. So like if you join 5 minutes before the contest, you might not get approved. So you will lose. Yeah. Okay. So the contest is hosted on VJudge, and this has some implications. I think there is no like clarification. Like you cannot ask for a clarification on VJudge. So I would like you to like ask me ask all the clarifications to me on Telegram, and in case there is a need for like public announcement, I will come up with something. And also, because like I don't know if you are familiar with VJudge, but VJudge is like not a normal online judge. It in fact it submits your submissions for you on another online judge. So like one thing is that there is, for example, no custom invocation. So what I'm trying to do is I'm trying to like always pick problems from only one online judge for one contest. So the runtimes are consistent. And a second thing is in many problems are like from some Polish contests. The statements are translated to English, but often, like for example, names of colors or yes, no is not translated to English. So you will have to like pay attention to like which character corresponds to which color. Sorry for that. Okay. So I think that's it when it comes to like technical stuff. Okay, so one more question: is it like decided who goes towards finals out of people here? Oh, okay. So one thing I would like to mention is that I'm going to World Finals this year, so I'm gonna meet some of you. Okay, cool. So now let's talk about like my insights on contest strategy. This is like by no means this is the like only source of truth and the only valid way to think about it, but like my coach told me some like advices, and I found some of them valuable. So like I'm doing roughly the same thing now. Okay, so the first advice is like about like problem statements, because on like many competitions you get 3 copies of each problem statement, like 3 copies of problem statements, and my opinion is 2 of them are like to be thrown away immediately. And now why? Because like you don't want a situation when there are 2 people thinking of like the same problem and they did not communicate about it. So by throwing away 2 copies of problem statements and like keeping only 1, you can do something like, okay, whoever holds the problem statement in his hand or like has it next to his notebook is like a mutex on this problem, and he is to think and try to solve this problem. I think like I personally experienced this unpleasant situation where 2 teammates were thinking about the same problem, and for example, one came up with a solution, implemented it, and like then the other person, oh, I know how to solve it, I'm gonna code it now. Yeah, this sucks, and like this is a very, like I would say, very low cost solution to making sure it does not happen. Another thing related to like problem statements is to try to avoid telling somebody the problem statement. Like, I know there is a big urge to like, oh, my teammate just read this 2 pages long story about kangaroos or something, and there is like this tiny amount of task. But like, in my opinion, there is like positive expected value in telling the teammate to read the statement himself, because like you can avoid a lot of mistakes in that way. Which are like pretty costly, and like most of the time you're not losing by 3 minutes of penalty, right? Which you will save on like reading. Like you will save at most that. So yeah. Okay. So another thing is about like communication in a team. So my opinion here is the less communication, the better. And like what I'm trying to say is that you ideally, for most of the contest, probably want 1 person to think about 1 problem, and the only topic of the communication should be who uses the computer now, or like who's gonna use the computer next. And like for example, if you watch a stream, there is this competition called Universal Cup. When you, for example, watch a stream from like Universal Cup finals with like top teams, you can see that many of them barely communicate. Like the only things they say is like, okay, I'm gonna like take the computer now. It's gonna take me 20 minutes to implement this problem. And I think that like this is the best way to like utilize your assets. By assets, I mean 3 people who can think independently on the problems. There are like some exceptions, obviously. For example, like if you know that like your teammate is super good at, I don't know, generating functions, maybe you can ask them, oh, can this subproblem be solved with generating functions? But like without this prior knowledge, asking your teammates about random subproblems of your problem is probably not a good idea. Because like they have to context switch from their task. The first thing is they need to waste time to like think about the sub problem which you just told them. The second thing is you need to make sure that they understood the sub problem which you told them, because maybe they will be solving a different problem because like I told about this earlier. And the third thing is like context switching, which is like bad for solving like deep problems. So the less communication, the better, except the computer, which is like also the important part. So one thing about like the computer usage is that top teams, which I know, practiced something like that during their trainings. Whenever somebody said, "Okay, I'm gonna like now implement this. This is gonna take me X minutes," they were noting it down on the paper, and like after the competition, they were reviewing like, "Okay, this took me an hour. Well, that means I did something wrong, right?" And what they like were trying to do is they were trying to make their estimations converge to like the real time that it actually takes them to implement this, because it really helps a lot if you have like better estimations, you know, shortest problem first and this stuff. Okay, so next problem, next thing here is like the psychological aspect of like submitting a wrong solution. So like I saw some people, and I myself had like this, in my opinion, wrong mindset for some time, that like submitting a problem and getting a wrong answer is like if it takes you 15 minutes to make sure it's good, or you can submit, then it's better to take 15 minutes, because 15 is obviously less than 20. And no, like that's just wrong, because like what you're gaining, like 20 penalty minutes are worth less than 20 thinking minutes, right? Because for those 20 thinking minutes, you can solve another problem, right? And the penalty is this number which will decide, like, maybe you will lose like one spot, but if like verifying something will take you roughly 20 minutes and even like 15 minutes, then it's probably more worth to just submit if you are confident, like any confident about whatever you coded. Okay, so another thing about communication is like the last hour of the contest, because like as I said, it is good for most of the contests to work more or less independently on those problems, but like when there is a like last hour or last hour and a half, you probably already experienced that an hour is not much, especially a last hour is like even less than the first hour. So you probably want to like take 3 minutes to discuss like what's the progress on all the problems you're solving, because there are like potentially 3 problems which you are solving independently, and try to like decide, because in one last hour, like it is usually very probable that you will be able to solve one problem. You maybe will be able to solve 2 problems, but solving like all 3 problems on which you're working in last hour happens like less often than you think when you like write down the statistics. So like you usually want to focus on less problems than you're working on, and then like you need some like experience to judge which problem is most likely to be solved by us. But yeah, another thing here is that one strategy I would say which one can use is that like when there is a team which like you personally know, and like you know topics they are good at, and you see some problem that was accepted by them really fast, you can like sometimes reverse the engineer. Oh, they are good at flow. This is surely flow. Like I did it 3 times and it worked. So okay. Yeah, so in like last hour or hour and a half, you probably want to focus on these problems. Yeah, okay. So now some like technical stuff, but like by technical I mean like coding preparations and more computer related stuff. So the first like one very big game changer in my competitive programming career was using, was like when I started to use sanitizer, I was like, why nobody told me about this earlier? Okay, so like quick survey, who uses sanitizer? Wow, not everybody. Okay, so when you're like compiling your program and like you have some undefined behavior, for example, you're accessing like out of bounds, but for example you're accessing only out of bounds like by one, then like it is very likely to appear to work on your computer, and with some probability not work on the judge. And like sometimes it even depends on like if the test is small or big, or even on compiler, like you are invoking an undefined behavior. So there is like a set of compilation flags which like you can add to the compiler, which means basically, hey, please compile this program in like a different debug way, which makes it like 20, 50 times slower, but you are very likely to spot many mistakes. So the flags are wait. Okay, so like dash f sanitize equals address undefined. This is the first flag. Like do not copy all the flags from the whiteboard to your notebook. Like just write one and Google like code forces compilation flags sanitizer or something like that, and you will have this long list of like compilation flags which you want to use. I'm just like gonna give you an overview of what those flags do now. Okay, so like this fsanitize address undefined is intended to like catch at runtime many, like I think it does not catch every undefined behavior which you can have, but it catches a lot of them. For example, if you access access an array out of bounds, it is like guaranteed to terminate and print you some message like runtime error out of bounds access at line, and give you like the exact line where you had out of bounds access. And, like this is awesome. Like this basically makes turns your C++ into Python during like your debugging session, and makes you less likely to do stupid mistakes. It also can detect signed integer overflow. So like no more submitting problem with modulo just to see, oh, I forgot to add modulo here, but all the samples are small. Yeah. So there are like more flags with about this like sanitizing and detecting undefined behavior. There is something like dglib cxx debug. This turns on like assertions in STL. So like the whole STL, std vector, std set have like some assertions made there, but like you don't want them on a production. You don't want to check for every like access to vector if it's in bounds or out of bounds, because like your program is now 4 times slower. So you want to have it during your debug, but not during like production or submitting. So this is nice to have. And also there are warning flags. There is flags WO, which means like warnings all, and this does not turn all the warnings, because this all meant like all but 30 years ago or something like that, and like we are keeping this for compatibility. There is also W, I think extra and more. Those flags will give you like a warning. For example, when you check for float equality, you probably never want to do that, but it's easy to do that by accident, and then like it might be hard to spot this mistake. Or for example, when you have some argument which you're not using, it will also warn you, because like this is often a mistake that you have some arguments A and B, and you are like using only A in formulas because I don't know, you mistyped or something. And it's like I find this also really helpful. So like in my team, the first thing that like we do on a contest is like obviously writing our like template, but those flags and like compilation settings are the part of the template, and the default workflow to like work with the task is to compile with those flags locally and run like everything locally with those flags, and we just have like a second compilation option list to like benchmark how fast is our solution or something like that, because as I said, this makes your solution way slower than it normally is. So one convenient way to do that is to there is a file called bash rc, and you can put aliases there. So like you can basically define your own commands, which will be then like usable by terminal. So you can say that like I want c sol.cpp to compile sol.cpp with all those cool flags, and that's what in my team is being done. One thing is that after you edit bash rc, you need to reset your terminal for the changes to apply. Okay, another helpful thing is hashes in your template code. For example, in like when you need to write a link cat tree or FFT, like some very long code in which you are likely to make a mistake, you can like set up your code base in a way that like there is a very short script which takes like source code which you have, removes all the white spaces, removes like all the resolves all the macros and stuff, and then calculates a hash of it, and you can put this hash in your like notebook with codes. So then when you write your link cat, which is I know 300 lines long or whatever, then you can like spend 1 or half more minute to write this hash script to so you can verify, okay, what I typed is 100% correct. Like, okay, it means it is the same as I have in my notebook. So you know that if something doesn't work, then it's not because this long code has some formula off or something like that. This is like also really helpful. I know that it might be hard to like convince oneself to spend this extra half minute. No, I'm super programmer. I'm not gonna waste half a minute to do that. But like in my opinion, it's really valuable, and I personally do it even for like shorter codes because it's like then saves you time when you have to like write much code. Okay. Okay, so I think yeah, I think that's all when it comes to like contest strategy, pro tips or whatever from me. What time do you have? Okay, so do you have like any questions regarding this? Yeah.
Is it worth it to learn about debuggers such as GDB?
Is it worth to what?
Use debuggers.
Yes, but not in a way you think. So, oh yeah, sorry. I actually now thank you for this question, because now I forgot to mention one thing. It's a debug macro, which is also very powerful in my opinion. So like you can have a debug macro which takes like few minutes to write at the beginning, but it is able to to print any STL container, including like nested STL containers. So like you have vector of sets, you do like debug file or whatever, and it will print you your vector of sets. And like this is awesome because one thing is like you're saving time on typing later when you have like complex structures like that. And another thing is you can make your setup so this debug macro only does anything in this like set of debug flags. So then when you submit to the judge, it's like this debug does not exist, right? Because the judge is not using your flags. So like it is really helpful in last minutes when you don't have to comment out everything in that way. Yeah, so regarding GDB, in my opinion, you should like, if the computer is not free, so like if somebody else wants to write some code, you should avoid debugging on a computer. And like how to avoid debugging on a computer. So one thing is that you want to like use as much printer as you can, basically. So whenever you're changing the person who's writing, you want to like print the code. No matter like how small the change was, you just print it. Like because maybe it will take a bit longer for this person, so you have this code now. Another thing is to like add those debugs before bugs happen. So like I'm actually not following this that much, but like I add at least some debugs like by default, even if even if the code is like not even compiling yet. So later when like we want to like switch the person on a computer, I run my code on some test, copy this like debug output and like paste it into the source code as a comment and print it and like debug by hand. But like back to your question about using GDB, it is useful because GDB lets you see, for example, when you have a segmentation fault, it lets you see on which line was the segmentation fault. And like now your question could be, okay, but this also lets you. Yes, but sometimes you only have a segmentation fault on a big test which you can generate it, and like it's too slow to wait for the big test to complete on these flags. So what you can do instead is you can compile with a flag like with your usual flags, but add ggdb3, which basically means that like your executable will have information about the source code. So GDB can like use this information to tell you more about what's going on. And when you have like a test where it does not work, where it's segmentation faults, you run. I will like wipe it. Anybody wants to? Okay. And you do like gdb /sol. This like starts a new GDB session with this solution outpend. Then you do run input file. This will like run your program with input file as an input file. And then once it's segfaults, you type BT, which stands for backtrace, and you will see like exact line on which something went wrong. And like sometimes this backtrace is like deep into, for example, some library, so you just like want to find the topmost like reference to your code right on this backtrace. And then Control D and Control D to exit GDB. So like, I for example have a muscle memory for typing this combo, but yeah, it is helpful for like debugging complete tests. Okay. Oh, okay. And one more thing. I will tell you, like, this is like a very random thing which does not basically fit anywhere, but this is like a trap for which I fell for and was debugging for hours, and I believe it's helpful to know that. So, who of you heard about ordered set, like GNU PBDS ordered set? Okay, and who of you heard about swapping those sets? Oh, okay, so very few people, cool. So the thing is that like when you have two vectors, like let's say this is like v1 resize million, v2 resize million. So we have like two vectors of size million, and now we have a for loop. For loop like I 0 to million, we do something like v1 random. Like we increment some random stuff on those two vectors, and then like here we do something which takes constant time. So like this loop has actually some effect, and then we swap those two vectors, and we do it a million times. So who thinks this code completes under 100 milliseconds? Like, this is not a trick question, but basically, it either completes under 100 milliseconds or over 10 seconds, right? And like, I'm asking, is it under 10 seconds? So who believes it is?
Both are vectors.
STD vector. Okay, so some people do, some people do not. So yes, it does complete on like, I don't know if it is required by a standard to complete to be like constant time, the swap of vectors, but on like same implementation it does. And like, how can it be? Okay, so how does the vector actually work? So vector actually inside it has some integer with size and some like some pointer. Let's say void pointer, like whatever, to the data it stores on a heap. And maybe some other information, but like roughly this. Probably also capacity. So how can we swap two vectors in a good way? We just swap those two values inside, and like since this is just a pointer to the stuff on the heap, it's constant time, right? So like it's not a problem. But like, how does this swap function know that it can do such things? So what vector does is it implements like a swap function, which is like a member function of a vector, which knows how to swap second vector into myself, and then I don't actually remember how is it like in details implemented, but it is a way to say, okay, so swap. Please use vector.swap inside, so it is fast. Okay, so now the question is, now let's say this v1 and v2 are those GNU PBDS statistic order tree, whatever. So who believes this completes under 2 seconds? Okay, who believes it does not complete under 2 seconds? So I think we have like non-empty set of people who believe it completes in exactly 2 seconds. Okay, so the answer is like the standard does not specify that because those GNU PBDS containers are not specified by standard. But all the implementations are so. For all the implementations are so. This is slow. This runs in like 1 SX to the power of 2. And why? So those containers also do implement dot swap as a vector, but nobody told this swap that it can use it. So like then default implementation of like swap is like it's some template t, like tc equals b, b equals a, c equals b, no, wait, b equals a equals b, yeah. So it just does 2 copies, and like that sucks, right? So the thing is, when you're using like some shady STL structures, please remember about using like s dot swap s2. This works in constant time. This does not. Okay, and yeah, and it's like crazy hard to find this bug if you don't know about it, because like you have something that looks perfectly reasonable, and like it's often like hard, not easy to come with a like test which produces such a behavior, because like it usually is being used in like some small to large merging, like those swapping of PDS sets. Yeah. So like I'm happy that I brought like a lot of delta, because few people knew, now everybody knows about it. Okay. Cool. Okay, so second trap, which I can tell you about, is when doing a binary search on floats. And you have something like, we want the absolute error or relative error to be at most 10 to the power of -6. So you can write a code while r minus l greater than, let's say this is epsilon, do something. Okay. So who believes this code is correct? Like assuming correct implementation of binary search here. Okay, and who is able to say why is it not correct? Okay, again, very good.
Numbers are too large, might be zero.
Yeah. So like, what actually might happen is that like float is not some like crazy magic. It is like basically what float stores is some like exponent, and it stores number in form 2 to the power of a times b, where b is smaller than like between 0 and 1, and there's also a sign. Okay, so like when dealing with those big numbers, we can run into a case that like 2 consecutive floats. I know there are no 2 consecutive real numbers, but floats are not real numbers. They are like some. They can only represent fixed set of values, right? So there must be some order on those values, and it may happen, like it actually happens, that for big values of a, because this b has fixed precision, right? Like it can, like there is some fixed distance between 2 consecutive b's. So it happens that for big a's, the distance between 2 consecutive floats can be greater than that. And we are screwed, like this will never terminate. So very lazy fix here is to count the number of iterations and say, if it's more than 100, 200, whatever, we just break. And it works, and we don't have to like write some formulas with relative precision, fixed, whatever. Okay, so any questions when it comes to this? Okay, cool. So now I think it is everything in this like introduction, and now I will talk about FFT and its applications, its many applications. Okay, so, huh?
I'd like to ask a question about your concepts. Will they have a specific theme every day, or will they be composed of like random problems? What is this style of the concept?
Like, neither of those. Like, problems are not random, they are selected by me.
Yeah.
So, no, like, I'm not I'm not like not willing to say that contest will have themes. Maybe it will happen that some contest has themes, but like I'm not making deliberate. Oh, it's an FFT contest tomorrow. But you can like what I'm trying to do is I will make lectures about topics which appeared on contests and like I'm not to spoil the contest, so lecture will be after the contest. So that's why like I'm not revealing the topics of the lectures. Yeah. Okay. Any more questions? Okay. So now like it's my question. So like first, who heard about fast Fourier transform? Okay, who heard about fast Fourier transform before I said fast Fourier transform? Okay, who like has fast Fourier transform in their like team library or whatever? Okay, maybe who does not? Everybody has. Cool. Okay, who is able to like implement a fast Fourier transform if they were given like a day and computer without internet? Oh, wow, we really quickly dropped, like, roughly 0 people. Okay, so I'm not gonna, like, waste your time by, like, spending too much time on theory, proving that this Van de Moor matrix is invertible, something. I'm, like, going to rather do more practical stuff. Of course, I will tell about, like, roughly about this, like, theory. And then like some cool applications, less cool applications, and yeah, and traps to which one can fall. Okay, so yeah, like I agree with like I know it was like a conscious choice of most of you, but for most of the problems you do not need to be able to implement FFT by yourself. You even do not need to know how it works. But there are exceptions. I will show it later. But yeah. Okay, so like like basically the what we want to do, like why FFT? So what we want to do is we want to be able to like solve the polynomial multiplication problem fast, right? And everybody knows like the n-squared algorithm with 2 for loops. Which is like surprisingly fast because like those loops can be vectorized and like sometimes you can pass n-squared where you're not supposed to. But okay, so like the idea is that what we wanna do is we wanna to because like how do you usually represent a polynomial? So what you usually do, you store a list of coefficients and say all the other coefficients are 0, right? So there is like, we can represent a polynomial in a different way, which also like uniquely identifies the polynomial, which is like, let's say the length of the polynomial is n. By length of a polynomial, I mean like degree plus 1, because it's like the number of coefficients. So let's say the length of the polynomial is n, and I claim that if you have a like a hidden polynomial of length n, and you give me values of this polynomial in in n distinct at n distinct values, then I'm able to like reconstruct your polynomial, right? Like if you give me pairs x I p xi where like xi not equal to xj for I not equals j. So I will be able to like reconstruct whole your polynomial. Who knows that fact? Okay, so this fact is like really useful here in this FFT. And now why? Because like multiplication of polynomials in this coefficient list form is a hard task. Like we cannot really do much, but when we have this representation of values at different points, so like let's say we have some polynomial P1 of size n, and we have it at n plus m, like its representation by values at n plus m distinct points, and some polynomial P2 and its representation by values at n plus m distinct points. Then what can we say about the representation of P1 times P2, where this time is like polynomial multiplication? So we can like trivially get it because for some number, for some like value, because like for some number x, it holds that like P1x, P2x is equal to P1 times P2, right? So like the difference here is we are evaluating first polynomial at this value, we are evaluating second polynomial at this value, and here we are evaluating the product at value, right? And this is the same, right? So this means that if there was some very kind man who, for polynomials P1 and P2, gave us this cool representation, then we can like in linear time get there, right? By just multiplying those two, provided that those x's are the same for those two, right? Then we can like in linear time go there. And now we need something to get back to normal representation, right? Okay, so like the whole concept of FFT is to be able to do this magic and this magic to like go into like value point value representation and go back to coefficient list representation. Like we want to become this kind man ourselves. Okay, and most the big idea here. Anybody wants to like write something from this, or can I wipe? Yeah, you can make photos like. It is also streamed and probably will be available on YouTube, right?
Yes.
Oh, okay. So yeah. Okay, so. So thing is, like we can not really easily evaluate polynomial at like given some list of values. It is not easy to evaluate it in this list of values. Like it is possible to do it faster than n square, but it's not easy. But like one thing that we can choose here is we can choose this set of values, right? So, like this, it does not like we were not relying on any property of those values except that they are different. So it's up to us to choose values which are convenient. Okay, so the trick here is to like when I said about like polynomials, you probably thought about polynomials with like real coefficients as a function from a real number to a real number, right? So what we are going to do here is to think about it somehow like in a different way. So we are going to work in a like with complex numbers, and it turns out it's easier to find like a convenient set in complex numbers. Okay, so maybe who knows complex numbers, like basic properties? Okay, who wants a quick introduction to complex numbers? Okay, so probably somebody still wants, so I will do it anyway. I mean, it's hard to like raise your hand. Yes, I'm the one who doesn't know, so like I will just do key facts really fast. Okay, so like basically we are like introducing a new value I such that I squared is equal to -1, and now like all our values are of form a plus bi, and this forms like we can divide such numbers. We can do everything with such numbers. What we expect from them. And the thing is that like one can easily check that product of two such numbers is also such a number. Okay, and there is some like a special set of those values. One more thing before that. There is also like a geometric interpretation of those values, which is like this is because real numbers can be interpreted as a point on a like number line, and complex numbers can be interpreted as a point on a plane, complex plane. So like the first is basically x coordinate, and the second coefficient is like y coordinate. Okay, so basically addition of complex numbers is you're adding those two like separately, so it's roughly it's as you added vectors or something like that. But to us, more interesting thing is the multiplication of complex numbers. So what happens when we multiply two complex numbers? So the thing that happens is that when we, because we can also represent a complex number as different pair of real values, which is distance from 0, 0 and angle from like this line, right? Like length of this and this angle lets us like uniquely determine this point. So what happens when we multiply two complex numbers is those angles are getting added and those distances are being multiplied. This is something like to prove it. It's a simple algebraic work. I'm not gonna do it now. So okay, and basically what I'm saying here is that we will like use that property to find a convenient set of values. And what I'm like proposing here as a convenient set of values is okay. So one, without loss of like generality, we can assume that length of our polynomial is a power of 2, because like we can pad it with zeros, right? And like it will not worsen the complexity since it's subquadratic. It's not exponential. Like it will be a polynomial complexity. So making the input 2 times bigger does not change the complexity. So and let this power of 2 be p. Okay, so we will pick a point such that the distance from 0, 0 is 1, and this angle is like 2p. 2p. Okay, I chose a bad value here. Let's call it b. 2p divided by b. Okay, so we want a property that, like, if you multiply this value, let's call it r. If we take the powers of r, those will be like this angle will get added and added, and at some point we will go to 1 and then back to r, right? After exactly b such multiplications. Is that clear? Any questions? Okay, and now why is it useful? Okay, so we want to write some recursive function which will evaluate our polynomial. Let's call it FFT, and we have like a point. No, we have coefficient representation of polynomial p, and we want to evaluate it in all those values. And return like a vector of values at r to the power of 0, r to the power of 1, r to the power of b minus 1. And a reminder, this is power of 2, right? Like, b is power of 2. Okay, so what we're gonna do is we're gonna represent p as p x, like every polynomial p can be represented as p0 x squared plus x times p1. Okay, so p0 is polynomial of only the even coefficients of p, and p1 is the odd coefficients of p. Right, just like concatenated as a coefficient list. Who sees that? Like, raise your hand, or like. Okay, so who does not see this property? Okay, so I'm gonna explain. Can the camera see this whiteboard, or? Okay, cool. So I will use a second whiteboard. It's like when we have our polynomial p equal a0 plus x a1 plus x squared a2 plus x to the power of 3 a3 plus x to the power of 4 a4. Okay, then p1 is equal to p0 is equal to a0 plus x a2 plus x squared a4, and p1 is equal to a1 plus x a3 plus x squared a5. Let's say that. Okay, so now, so those are like the even coefficients, and those are odd coefficients, right? But like those x's are from 0 to just going by 1, not by 2. And now when we put x squared inside, we just like make space between those coefficients, right? And multiplying this by x like shifts it, and addition puts it all together. Is it clear now? Mm-hmm. Okay. If you have like any questions at some point, just please raise your hand. I will answer. Okay, and why is it helpful? Because this means that if we evaluate p0, like we have this set, let's call it SB. If we want to evaluate p at SB, it is sufficient for us to evaluate p0 and p1 at squares of values from SB. Right? Because we only put squares here. Right? Okay, who agrees with this statement?
But don't you have to use the x place multiplying p1?
Okay, so let me try to say it again. So let's say that some nice guy gave us p0 at like squares of SB and p1 at squares of SB. Okay?
Oh, okay.
Then like we can in linear time get then we can at linear time get p at SB, right? At every point. Who agrees with this statement now? Okay, I see it's not clear. So, any questions? No. Okay, but like not everybody raised your hand. So, can anybody tell me what's not clear here? Okay, who wants me to explain something once again? Yeah.
When you split that polynomial in p0 and p1.
Yeah.
What does the x squared inside the argument of p0 mean?
Okay, it means like when you have some like polynomial of variable x, you can create a new polynomial which is like the old polynomial where we substitute x squared for every x. So for example, if we have polynomial 2 plus 7x plus 10x squared, this is like px, then px squared is 2 plus 7x squared plus 10x to the power of 4. Right? Like we do a substitution where we put x squared at place of all the x. So like what it does to the like list of coefficients is it makes it like it puts 0 between every two coefficients, right? Because all the exponents get multiplied by 2. Okay, so now this means that like to get p at SB, like at every point of SB, we only need P0 and P1 at points of squares of values from SB. And now is like the nice moment when the choice of SB is useful. So the thing is, the set squares of SB is equal to SB minus 1. Who agrees with this statement? Okay, so basically what happens is we had let's think what does it mean to take square. To take square it means to like multiply with itself, so it means to multiply the angle by 2, right? So if we operated on multiplies of 1 2 to the power of kth angle, right? Now if we take squares, those are only multiples of 1 to the power of 2 to the k minus 1 of angle, right? So, yeah?
Wouldn't it be like b divided by 2?
B divided by 2. Sorry, b is power, yeah, my bad. Yeah, sorry, I forgot it's not an exponent, but power of 2. Yeah, so basically set of squares is like a smaller set. Okay, and why, what advantage does it give to us? So it means that like when we do it like recursively, so we have this FFT for this polynomial p, we want to call FFT on two smaller polynomials, p0 and p1, right? And then do a linear work to get back, to get our result. So this is like Tn equals to Tn divided by 2 plus, 2 Tn divided by 2, because we split into 2 halves, right? And evaluate a smaller problem 2 times, and then do a linear work. So this is n log n. Right? And this makes us able to evaluate this polynomial in enough distinct points in a short time. Like n log n is fast. Okay. So now the thing is, how do we go back? Going back in code is actually very short. So what we do is when we want to have our inverse FFT of P, we do FFT on P, then we divide all the coefficients by n, and then we do a reverse from the first to the last coefficient, skipping 0. And proof of this property, it uses the fact that this is actually it means it's a multiplication of some, this FFT is a linear transform on some vector. So we are multiplying some vector by some matrix, and when we consider how does this matrix look like and see its properties, we can derive that this is basically taking the inverse of that matrix, multiplying by the inverse of that matrix, which means going back to the list of coefficients. And I think you don't need to know the proof of this. I'm yet to. I saw the tasks where you need to know how FFT works to solve the task. I don't think there is task where you need to know this. I'm waiting to be surprised, but yeah. Okay, so like, so to like quickly go over it once again. What do we do to multiply two polynomials? So we assume like both are of size n, which is a power of 2. We oh yeah, and like here is one more thing. Because the result polynomial is of size like 2n, we need to like evaluate those polynomials in like 2 endpoints, right? Not just n. But like, yeah, this is a technical detail. So we just evaluate those two polynomials, do like a pointwise multiplication on those lists of values, and then do like the inverse FFT to get a product of two polynomials. Cool. So we are able to multiply two polynomials really fast. Okay. So now it's roughly done. So we're gonna have a coffee break. It's half an hour, right? And then we have 1 more hour of lecture, right? Okay. So then I will tell you like. Basically, I will show you many like problems involving FFT, from simple ones to crazy ones. Silence, please. Okay. Okay, so now I'm gonna tell you about like some example problems which can be solved with FFT. Actually, quite many of them. Okay, so like the first thing is like I told you that like FFT is used to multiply polynomials, but like let's forget those are polynomials. Like what actually is important is like the convolution operation here. Like is the same thing as product of polynomials, but like I will basically tell you how to think about it to make like the whole process faster. So like I will be introducing like many variables, and like those variables will be either like numbers or vectors of elements. I mean sequence of elements, and like by default this sequence is like of infinite length and is padded with zeros like infinitely. Okay, so because that's basically a polynomial, right? A sequence of values, coefficients, and padded with zeros. And like addition on such vectors is like easy, right? It is well defined as addition of polynomials. And convolution, which I will like denote as a star. So this is like the convolution operation, and C equals AB. It means that like C at index I. This means like let's take ith element of the vector, right? Like I hope it's intuitive what do those symbols mean, right? Is sum over all j's from 0 to I okay, so we are saying that like if coefficient of a convolution is sum over pairwise products over like all the pairs of indices such that their sum is I, right? And this is exactly like the product of polynomials, right? When we think about coefficients. But like I'm forgetting about like polynomials here, not to like think about some functions from numbers to numbers or something, right? It's just like an abstract sequence of numbers where now we also have a fast operation of convolution. Okay? Like who understood what I said? Cool. Okay, so the first task is like okay, maybe not. Let's not wipe it. Okay, so the first problem is that we want to check how many solutions are there to the equation 3 to the power of x plus 5 to the power of y equals 7 to the power of z modulo m, where m is like less or equal 10 to the power of 6, and like x, y, z should be like less than m. Okay? Okay, I'm just like gonna ask you, who sees how to solve this task immediately? Okay.
Sorry, in which time we should solve the task?
It's up to 1 million. So. Okay, so nobody knows how to solve it. Okay. Like we don't. Okay, this modulo is that this equation should hold modulo, not the result modulo n, right? Okay, so okay, so now how do we like approach this task? So we can generate a vector of like vector, let's call it A, which stores AI like is number of x's, such that 3 to the power of x modulo m is I. Okay? Is like this definition clear? Okay, and we can do another like such a vector b for 5 to the y and c for 7 to z, right? Okay, so what can we do now? Let's think, what does a convolution B mean? It is some vector D, and it tells us in how many ways can we pick two indices from I and B, such that sum of the indices is equal to I. I'm talking about the I. In how many ways can we pick index I, such that like sum of those two indices is I, and we will like take sum over products, right? Okay, so what does it mean? It means that if we have some value, let's value here, we are like considering all the possible ways to construct some I out of those two like modulo residues, right? Because like if we can have a residue 7 in 3 ways from this, 3 ways to get 7, and here we can have we have 5 ways to get 1. It means that like surely there are 15 ways to get 8. Like just this information generates us 15 ways to get some 8, right? Okay, so and now we are doing this with everything, right? By our convolution operation. So this basically collects for us all the information that we want. Like from the left side, we know in how many ways can we get this sum of those residues modulo, right? We will need to like because this sum may exceed the modulo, right? But like it does not matter for us. We can like fix it manually, right? Because like when we pick like here when we pick m-1 and here when we pick m-1, then like the sum of those two residues will be 2m-2, right? But like we can just manually put it in a like this modulo m bucket, right? To have like values modulo. So like just take the indices modulo. So we have for a left side, left-hand side, in how many ways can we obtain some values of a sum, right? And now we calculate, we have this vector for C, right? And we can easily just like sum over d I times ci, because it means like in how many ways can we get some like get some I on the left hand side times in how many ways can we get some on the right hand side, right? And this is like our answer. Okay, so like okay, sorry, I forgot to tell one important thing here, because like here we assume that like this convolution operation happens on some like magic numbers, some like big integers, so we can do whatever we want, right? And like that's not the case. Like usually, okay, here you can actually store the answer. Like the answer is at most 10 to the power of 18, right? But like in some combinatorial problems, it is not true, and then you are usually asked to get the answer modulo 2 to the power of 23 times 119 plus 1, also known as 998 244 353, I think. Okay, and like, why this number? What does it have to do with FFT and modulo? What happens? Okay, so like when we are doing this FFT on like real numbers, we wanted to choose a set such that like set of squares is 2 times smaller, right? Such a set, like if you wanted to have a meaningfully big size of a set, it's impossible to do so in real numbers. Like we can get 1 and -1, and I think that's the biggest thing we can get. We had the construction how to do that in complex numbers, but how do we why do we have this modulo here? Because for some modulos, like more specifically for modulos where like the size of the ZP cyclic group is divisible by like big power of 2, we can also find a cool set of values. So this means like for this modulo, there exists a cool set of values. You don't need to know like how does this set look like, nothing. Like it's in your library, right? So this modulo is here because of that, because it's like easier to implement a convolution with coefficients like modulo this. But like, okay, so back to this for a second. So if there was a modulo like 998244353, we could just like use this. This is called entity, and it's number theory transform, number theoretical transform, whatever. Yeah. So if there was like this answer had to be given modulo 998 this, then like we could just use this entity, right, to do those convolutions. Like those are 2 separate modulos, right? This modulo is modulo used in this equation, but this modulo is modulo for our answer to simplify the calculations. Okay, so I will talk a bit more about like this because like there are a few important technical details about like FFT and its usage on contests. Are there like any more questions to? Yeah.
On this specific example, like m goes up to 10 to the 6.
Yeah.
Wouldn't like FFT have some precision issues, like on the A times B?
I just said we are using entity because.
No, like on your first example, like.
Here.
Yeah.
Yeah. So like.
The answer is not modulo.
No. I said let's say it is modulo.
Oh,
Yep. Yeah. I'm gonna talk about precision issues in a second.
Sorry, I have a question.
Yeah.
I didn't quite understand how we work with that 2m minus 2 case. So, like, what happens like when like how do we properly match up those indices?
Okay, so like if there is an x such that 3 to the power of x is m minus 1, and there is a y such that 5 to the power of y is also m minus 1. Okay, so this like when we are working modulo, it means like this information is the same information as like there is a way to pick 2 such that the sum is 2m minus 2 modulo m. Like this is some number less than m, right? And we just like it's just this.
But like, how do we stick it into the FFT?
Okay, so like you do FFT first,
Yes.
and then normalize your output of this FFT. Like you get some output, right, some vector, and you need to say, okay, if index is like bigger than m, let's like put it in a smaller index. Okay. Okay, so back to those like technicalities in this FFT. Okay, so like here we considered like we do it modulo with cool entities that does it for us, but like it's not always possible, and sometimes the problem setters are evil, and the modulo is not nice, and like how to handle that. Okay, any more questions to this task? Okay. Okay, so the thing is, when like implementing this FFT on complex numbers using floats, we need to like because like let's say floats have unlimited precision. Okay, so what we could do, we could and we want to do this convolution modulo this number, for example. So what we could do, we have on an input, we have like two sequences S0, S1 on integers, which are like integers less than modulo. So how do we do this convolution? We like the coefficients are like integers less than modulo, right? So we like rewrite it to another sequences f0, f1, which is like the same sequences but on floats. Then we do like this FFT on floats. We get our result RF on floats, and then like we for each float, like I'm assuming like some magic unlimited precision stuff here, we calculate its value modulo m, right? So we get our final result on integers less than m, right? And it's like this, like we treat this part as a black box here. We don't care what's going on here. We put sequences of integers from 0 to mod, like less than mod, and get like convolution with like all the stuff resolved for us. Okay, cool. So, but it's not the reality, right? Like floats do have limited precision. So, okay, it's so what is like the limit of the precision here? So empirically, because here in this process, we like forget about the fact that we have a modulo here and like calculate this convolution like without modulo, and then we take a modulo here. So we need to estimate how big can a value here be. So when we calculating some Ci, which is I have it there, which is the sum. So this can be up to m. This can be up to m. And we are summing n some such products, right? So like this can be up to n times m squared. Okay, so like a rule of the thumb is if this is bigger than 10 to the power of 14, it won't work. If it's like close, then like it may not work. Like I don't know. I don't have a proof that it works, but like empirically, roughly there is the barrier where it stops working. If it's like way less, if it's like 10 to the power of 12, 10 to the power of 10, then like sure, no precision issues will be there. Okay, so how to handle bigger integers or like how to fix that? So because like if this m was small, we would be really happy because this n is usually up to 1 million, right? We won't do a convolution on like a bigger vector because it's like n log n already. So we want to decrease m, and like also decreasing m gives us like better profits here. So what we can do is we can say, let's say we have some like vector of values a is like some vector of values up to m. So ai, wait, I'll pick another. ai is like less than m. Then what can we do is we choose some value s, which is roughly square root of m. And we can say that a is some a0 plus s times a1, where, okay, so now here's like, I'm really heavily overloading operators here. This is a vector, this is a vector, this is a product of a number and a vector, so we are multiplying every element, and here we are adding two vectors, right? Okay, so what do we gain here? if we want to multiply two such vectors, we have like a0 plus s times a1. Oh, sorry, one important thing here is that all the numbers in a0 and a1 are less than s, right? Because like this is a square root, so here is like value divided by s, and here is value modulo s, right? For every position. So like this sum matches the values on the left hand side. Okay, so if we wanna calculate this product, b0 times s b1, what do we get? We get a0 b0 plus s a0 b1 plus b1 b0 a1 plus s squared a1 b1. Okay, but like now all those convolutions happen on like vectors with values smaller than s, right? We just square rooted the range, right? So we can handle bigger values that way. Is it understandable? Okay. And in that way we can perform like convolution with arbitrary modulo. Like we can do even like more splitting of precision and stuff. But like those are the technicalities. Usually you should have like in your library some codes with like description. You can use this only if some constraints, right? And you know when to use which code because of that. Okay, but like for any questions to that? Yeah.
I didn't understand the last point where you use S. What polynomials do you ultimately multiply in FFT? What are the polynomials?
Okay, we are doing 4 multiplications here, right? And all those, like this and this, all the coefficients less than s, right? So you do all of that. Now we have like better precision, right? And then when you have values, then you can like on integers calculate the value of this expression in every point, right?
You do FFT 4 times.
Yeah.
Okay, understood.
Yeah.
This means that if you are able to decompose two vectors A and B into that form, you're able to do this multiplication with a better precision, right?
I mean, yeah.
What I was going to ask is, how do we find this A0 and A1?
Okay, so A0i is AI modulo S, and A1i is AI divided by S. Okay. Any further questions? Okay, cool. So yeah, there are like various ways to increase your precision, but like just have good code in your library and don't care too much about it. From now on, we are like assuming all the calculations are modulo this, and like we don't care. Okay. So second problem. What's the time? Okay. Second problem is let's say we have two strings, s1 and s2, and those strings consist of the characters A to Z and star. Oh no, that's question mark. And now what we want to do is this is like a pattern matching problem. Okay, maybe I will rename those strings. So we have like a text and we have a pattern, and like we expect the pattern to be shorter than text. And we want to find all the positions where pattern matches the text. So like those characters work normally. So like X can only match X, but question marks can match whatever. Okay?
There will be question marks both on the
Yeah.
character and text.
Yeah. They can match like whatever. And the question is, how many matches are there? Like, in how many ways can we choose like when we have a text, we want to like we choose a position at which we start putting a pattern and check if it matches. Then like we choose next position and check if it matches. And like we want to know how many times will it match. Okay? Any questions to like a problem statement? Okay, so now, yeah. Okay, so here, like, as the person solving this problem, you see that, and like, okay, they only ask for a number of matches, and like, here's a dilemma. Like, do we need to actually know where those matches happen or not? And like, as for me, it is like pretty intuitive. Like, it's very hard to imagine a solution which does not explicitly calculate the positions, yet it's able to tell the number. So like the solution is actually able to like tell for each position if there was a match or there was no match. Okay, so how do we go about it? Okay, so let's think about something simpler. So let's say there are no question marks. Then like, sure, that this problem can be solved in a linear time, but we want to do it with FFT. So how can we do it with FFT? So we will actually calculate something more valuable, which means for each position, for each like starting position, we will know how many characters will match if we submit, like if we put our pattern here. Once more, there are no question marks now. Okay? Is it like all clear? Cool. So basically, we will okay. So we will do this thing independently for all the characters. Okay? So like for all the characters, run some algorithm which we want to run some algorithm which counts like the matches of those only like among those characters. Like only among one type of the character. Okay, so let's have some string a b b a and a. Okay, so now what we want to do is we want to construct like vectors. Like let's say we are doing it for the character a. It's like analogous for all the other characters because they are indistinguishable, right? So we want to construct a vector which is 1 if and only if there is this character at this position. So so here it will be 1, 0, 1, 1, 0, 1, and here we have 1, 1. Okay, so what we want to do here is for each position, like let's let it the result vector. We want to have, and this will be A and this will be B. We want to have some for j equals 0 to infinity. This infinity here is because I'm lazy, and like I'm assuming like if you access out of bounds it's 0, so like it will 0 out. Okay, so when there is a match, so we want I plus j times b j. So this means we take like this literally simulates like the naive algorithm which would count us. So like this means, okay, there is some, we want to calculate the answer for the offset I, right? So we for all j's, we consider 0th character. So for 0th character, we want to check this character at offset I with 0th character of B, right? And then for for next, we want to check with next, right? Is it like all intuitive that this is the same thing? Okay, cool. So does this look like similar to something? Like it's nearly the definition of a convolution, but we have something else here that like it can be rewritten as some j0 infinity. Because like the convolution was wait. The convolution was I is sum over all j and k such that j plus k is equal to I, j, b, k, right? Like it's the same definition. We want those two indices to like the sum of them. We want it to be this index, right? This index. Cool. So here it's somewhat similar, but we have j and k, and we want j minus k. Wait, b k, j minus k to be equal I, right? Like this is exactly this sum. Any questions up to this point? Cool. Okay, so what we want to do is we can. Okay, so how do we do that? Like how do we translate one thing into another? So what if we had a vector b prime such that b prime at the position I is b at the position minus I? Yeah? Like if we supported like negative indices, then it all works because like here you have a difference, but it's the same thing as like a sum with minus. So in practice, what we do, we do something like we want to have this b prime vector, but we don't want to like mess with negative indices, so we offset everything by n. So we have what we actually do is we take some b's, I is b n minus I, right? And then it's the same thing. Like this means that it's a sum over all jk such that a j times b's k and j plus k is equal to
N plus I?
I think n plus I. Yeah, I think so. But like maybe there is some off by one or something. But like the key concept is this, right? Okay. So cool. So we solved something which can be solved by 5 lines linear algorithm by FFT. Okay. But how do we like utilize this knowledge to solve the version with question marks? Okay, so like this was just to like showcase that like this matching can be like done by a convolution, and like here we could do this with for all characters, then sum those vectors, right? We have an answer. But like what we want to do in this whole and this works in like 26 and log n, right? Because for each character. Okay, but this the funny thing is the solution for our version with question marks will be n log n randomized. So what we're gonna do is we wanna do solve like the like negation of a problem. So instead of checking where there is a match, we will check where there is a where is there not a match. Okay, so what we're gonna do is we're gonna pick for all the characters we want to pick, we want to have some function which maps f like a character to random value from like 1 to n minus 1. Like we just pick at the beginning some sequence of random values, okay? And what we're gonna do is we're gonna prepare a vector. This will be some like, let's say it's some array f. And now for our string, we will like for string a, b, b, a, b, a, and a, b. Okay, what vectors we're gonna prepare? We're gonna prepare vectors where like we pick the corresponding value from the f for each character. So here we have like f for a, f for b. Okay, and here we pick the inverse, like modular inverse, for all of those values. So to the power of -1, f b to the power of -1. Okay, and what do we do with question marks? For question marks, we just put 0. Okay, and now I want to do like this trick with convolution as we did previously. Okay, and what will happen? So whenever there is like a character matching with a character, the product of two values adds to the position. And what's the product if two character matches? It's 1, right? Because we pick the inverse. So if there is if there is a match on this position, we will have sum of those products. Sometimes we multiply by 0 because it's a wild card. So if it matches, then the sum should be between 0 and like length of pattern, right? Because we are, if it matches, we add zeros or ones on this position. And if it does not match, well, if there is at least one mismatch, we multiply some two random values, modulo 998, etc., right? So like, we might end up with value actually in this interval, right? But like, I think thanks to I don't remember the name of this lemma, but there's like this famous lemma for proving that doing this enough times with new random values and like checking if there was at least one mismatch for some random arrangement will give you like algorithm which gives a correct result with high probability. Okay, any questions? Cool. Next task. Okay, so let's say we have a tree, unweighted, yeah?
Excuse me, for the last approach, you can have any alphabet?
Yeah, and I mean, okay, if the alphabet is too big, then like the probability of, by accident, like the proof of the probability of being correct might get trickier. But yeah, like if this like modulo is so large enough, like yeah, sure, you can have any alphabet.
Thank you.
Okay, so we have a tree without like any labels, any weights, nothing, and now we want to like yeah.
Sorry, about the other problem.
Yeah.
Is there no like deterministic way?
Is there a deterministic way to do that? So like one thing that you can do is you can do it on floats. Like instead of taking the inverse modulo, you can have like some value and its inverse. But like you need to be really careful with precisions and proving that. But like I think that for the English alphabet, you can do it in a deterministic way on floats. For like let's say length 100,000. But like well, for longer, I don't know. Okay, any other questions? Okay, so we have a tree, and of size n. And now we wanna, for each I from 1 to n minus 1, we wanna know how many paths of length exactly I are there in this tree. So like answer I is count of paths length I. Okay, who understands the problem statement? Cool. Who like knows this problem or sees the solution immediately? Okay, few people know this problem. Cool. So many people will actually learn. Okay, so here like we are aiming for n log squared n solution. Like we are outputting n minus 1 values, right, for each like length. One like side note here is that if we were to output only one, like if there was some parameter k and we want to just count paths with length exactly k, then we can do that in linear time. But it's like exercise for you. So let's focus on this problem. Okay, so how can we approach that? Okay, so who heard about centroid decomposition? Cool, everybody. So we're gonna do a centroid decomposition. So let's say we picked a centroid, and we have some like subtrees here. So with centroid, we wanna like consider all the paths that go through the centroid, right? And then we like call ourselves like our function recursively on those subtrees, and it's all cool and good, provided that like we can do this phase in like fast enough time. Okay, so what do we actually want to do here? Let's think about it for a second. So we will like count separately all the paths which start at centroid and end somewhere. We can like in those subtrees we can do that in linear time, right? So now for all the other paths, they are of a form. You pick two vertices in two distinct subtrees and take the sum of the paths, the sum of the lengths of the paths, right? Okay, cool. So this it sounds like we want to do some convolution-like thing here. So what we can do is for every subtree we can create like a vector which tells us vi. It's vi is for like if subtree and vk for k subtree. I is like number of paths centroid to something length I. So it's basically we count how many paths from centroid to something are there in the subtree, such that the length is exactly I. Okay? Okay, so like let's for a second assume that the degree of the vertex is bounded by some constant. Let's say 3. Then like we basically have a solution instantly, because what we want to do is let's say we have like this vertex and have 3 subtrees, and we got those vectors v0, v1, v3. Like then the answer is like what we want to add here is we take a convolution v0 times v1 plus v1 times v2. I did one. Okay, yeah, plus v2 convolution v2 v0. Yay, right? Because like in that way we are counting number of ways to choose some path of some length from one subtree and some path from some other length and from another subtree, right? And so we just adding it up all together. Okay, but like here we assume that like the degree is bounded by and now like I claim that it already works n log squared. And why? Because like we have n phases of like this centroid decomposition. We will consider all of them separately, and like no matter what's the like size of those, I mean, no matter what's the size of those subtrees here, the sum of sizes of those vectors is bounded by size of this tree, right? So like we do like linear amount of we do a multiplication on convolution on vectors, which sum of sizes is some constant time size of a tree. So it's like size of a tree log size of a tree, basically. Okay, but what if like number of if a degree of vertex is not bounded? So what do we actually want to calculate? Is sum vi vj for I less than j. And this is half of a sum I not equal j vi convolution vj. Yeah, question?
I mean, I think I know how to do it.
What?
I think I know how to do the.
Cool, how to do that?
Well, you take the sum of everything and multiply it with itself, and then add the squares and subtract it.
Yeah, yeah. So like, yeah. What's your name?
Adrian.
Adrian. Adrian. Well, what he said here is that this is equal to okay, sum vi squared minus sum vi squared by 2, right? Because like we subtract like the convolution with the
ones that
we
the path to itself.
Yeah, sure. Any questions here? Okay, cool. We have 10 more minutes. I think we will do one more problem. Okay, so let's say we have n elements. Okay, we have some items. We wanna like buy some of the items, and like there are n types of items, and like each type has its size. Size I is less or equal to 5, and it's like at least 1, and has some number of variations. Where like we can pick a color of the item, and like for each item there is some like number of colors which this item may have, and it's like up to a like 10 to the power 9 and at least 1. Okay, so let's say we wanna like buy some items from the store, but like we can only have total size of items up to m. We cannot carry more, and each type of item, for each type of item, we can get like at most 1 of it. So like, if there is some item which has 2 variations, we can either take like, do not take this item, take first color, or take second color. Right? We cannot take both colors of the same item. Okay? And n is up to 10 to the power of 5, m is also up to 10 to the power of 5. Okay, so like basically this problem is like some knapsack, right? It can be solved with like knapsack in n squared by like doing simple dynamic programming. Okay, but how to do it faster? So the trick here is to like express knapsack by multiplication of polynomials / convolution. So what we gonna construct here is like vector which corresponds to a choice for each item. So when we have some item described by two parameters, we pick a vector which on position 0 has 1 and on position Si has Vi. This means that like there is one way to pick, like in one way we can pick no item which has size 0, and in Vi ways we can pick one item which has size Si. Okay, and how do we make the answer out of it? So my claim is, and let this be some like Ti. So my claim is answer is like this is iterated convolution over Ti. Who agrees with this statement? Okay. So who has some like question or something like that?
What was S? The type of the item?
S is size of the item.
Ah, size.
So like when we calculate this, we will have like okay. So let's think about like polynomials. When we will have when you have like 1 plus x to the power of 4, 5x to the power of 4 plus times 1 plus 3x squared. When you like consider all the like sequences of choices, right? Then this product, like when you then like the exponent near the x will tell us like what's the size of this choice, right? Because it's a sum of exponents, and the coefficient is a product of coefficients near those x's, right? So this like corresponds to like a product of choices, right? And this iterated convolution basically calculates that. But like now here is the question: how to do it fast, right? Because this iterated convolution, like if we did it naively, so like we had some answer and we multiply it by something, then we would get like n squared, because because when we get to the half of our multiplications, then this is already of size like m divided by 2 at least, right? So now multiplying it by one more polynomial takes like the complexity is the sum of sizes, right? Like sum with log, but like for our considerations, it's the same as if it was a sum. Okay, so the trick here, like, is to what we need to like exploit here is the fact that this size is small always. So this means that like when we take some like k items, then the total size of the choice, like the total size of this answer vector, is linear in terms of k. So we can do a divide and conquer over all those like ti's, right? And like recursively compute products of those subtrees. So like and we know that like if there are like here we want to have product of n. So what we do, we get a product of n divided by 2 items and another n divided by 2 items, and we know that like the size of those is always smaller because like there's this bound, and then we do like FFT here to combine this, and yeah, that's it. Okay. Any questions? Yeah.
The complexity in the end would be something like n log squared.
Yeah, n log squared, exactly. Yeah.
The exponents correspond to the size of
Yeah.
the element, and the value is the coefficient.
Yeah, the value is the number of colors, right? Because like when you multiply things, the exponents get added. So like you want to put some additive trait, like you want to put information about something that you want to add when you combine elements, right? So like you put information about sizes. It's like a natural choice here, and the coefficient get multiplied. So like this like perfectly matches what we want to do. If you have like if you can choose independently colors of 2 items, it's the product of numbers of colors, right? So like it does exactly what we want it to do. Okay, and any more questions? Okay, so I think that's it. Thank you.